Right, guys. I'm going to try and focus on practical and required practicals. I'm not going to work through any of the calculation. I'm going to try and give you some of the information that you need with regards to sort of improvements of a practical, things to look out for, the kind of questions that they tend to ask, which is more associated with doing the practical. So let's start with looking at titration. So some of the improvements that they often ask about. So they might give you a series of instructions, and then they ask you to highlight any improvements that you can make in that series of instruction. Now often, this will obviously depend on the information that they give you, but often what's left out is when you're making the standard solution, you've got to make sure that every single solid is accounted for. So one of the improvement is being able to wash out the solid from the weighing boat. So often students leave some of the solid, so you've measured out the solid and you either don't reweigh it to account for the solids lost, or you don't wash out the weighing boat. The other thing is you usually use a glass rod, so you need to make sure that you wash the rod that you use to make sure that any solid that might be left is accounted for. So wash the rod into the flask, so often that is left out. The filter funnel, so wash the filter funnel. So a lot of these is to make sure that all the solid that you have put in the solution, all the solid that you have put in the volumetric flask is accounted for. Other things to look out for, you've got to make sure the solution is mixed. So mix the solution by inverting the volumetric flask. So you invert it a few times to make sure that all the solution is completely mixed. Okay, other things to look out for. If you leave the funnel on the burette, now the problem with that is, the issue with that is what happens is if you started the practical, some of the solution left on the funnel may trickle into the burette. So what would happen there is you started the experiment and there's a drop of solution still left on the funnel, and that trickles in after you've started the practical. So that's all, obviously that will give you inaccurate results. So that's often a question. Other things like when you get to the end point. So end point, what you're doing is you are looking at improving the accuracy of the end point, so by going dropwise. So dropwise is doing one drop at a time, and that will improve the accuracy of your end point, and obviously making sure that you do a trial run to identify where the end point is or close to, and then you can slow your burette down onto dropwise. Okay, other things, conical flask. Why do we use a conical flask in an experiment? Okay, another thing, looking at a conical flask, so some of the things the reason why we use a conical flask, it allows us to easily swirl, and that's why, and then also narrow neck prevents splashing. So because you're swirling your solution to make sure that the solution is mixed, if you've got a narrow neck, that will prevent any splashing, and therefore compared to say a beaker. So that's why we use a conical flask. Um, Other things to think about: errors. So when we working out errors, they will often give you the individual errors for the equipment that you use. But what you need to remember is that if we are talking about an error associated with a pipette, you multiply the error by 1 because you only use the pipette with one measurement. So you make up to the line 25 centimeters cubed, so it's only one measurement. Compared to a burette, you make two measurements there, because what you're doing is you take the initial volume and then the final volume. So whatever the error is, you have to multiply that by 2 if we're talking about a burette, and multiply it by 1 if we're talking about a pipette. And then the other thing around errors is bigger volumes reduces error. Because the error is a set point, it might be plus or minus 0.15 or plus or minus 0.05. Whatever the error is, the bigger the volume, the smaller the error becomes, because the significance of it reduces. So if the question is around how can you improve this, having bigger volumes by changing the concentration will improve the percentage error that we are talking about. Other things associated with titration, say we've got indicators. So what makes a poor indicator? A poor indicator is one that hasn't got a distinct sharp end point. So if there's no sharp color change, then that's not a great indicator. You need a specific end point. So if there's no specific end point, then that's a poor indicator. I've seen questions where, and often this happens in lessons, where a titration you've done and you've overshot the end point. So if you overshoot end point, what does that mean in terms of your results? What's happening there is, when you overshoot the end point, your volume is bigger than it should be. If the volume is bigger than it should be, then the number of moles is bigger, and therefore that's how it affects your calculation. Now if you then take that mold and you're working out, say, the X number of moles of water in, say, sodium carbonate, then if your number of moles of sodium carbonate is bigger than it should be, then the number of moles of water will end up being smaller than it should be. So that's how you'd link the two together. So that's often, I've seen that come out. So these are some of the points that you would associate with titration, and some of the practical things that you need to think about. Okay, next practical, we're looking at, say, enthalpy of combustion, or looking at a cooling curve. There's a number of sort of different ways of doing the same practical, but often, so it's practical 2, often it's this graph where you've taken a number of data points, and then you have drawn this graph and to see how this cools. Now you've got to remember, with these graphs, you draw a line of best fit there, you draw a line of best fit there, and then at the point at which you've added your solution, you work out your delta T. So you've got to extrapolate that line, and then that will give you delta temperature, delta T, and you use that delta T to work out Q. Few practical points. Why do we have this 3 minutes before or 4 minutes before mixing your solutions together? The main point is why you do this is to ensure that the temperature is the same as the surrounding. So the temperature of the solution and the surrounding is steady. So ensure same temp as the surroundings. So it's a steady temperature. So that's why we measure the solution for the first 3 minutes, and on the 4th minute you'd add the other solution. That causes an exothermic reaction, the temperature goes up, and then you take the temperature every minute as it cools down, and then you extrapolate that line to work out delta T. A few other things. Why do we stir? So I know this is obvious. So the stirring is to ensure uniform temperature. That's why we need to make sure that the solution is stirred. So here the stirring could be a point of contention because stirring sometimes isn't uniform. So to ensure that it's uniform stirring, you can get magnetic stirrer. So a magnetic stirrer, what it does is it's got a small piece of metal and it just rotates continuously on a stirrer, and then that will be uniform, and you can adjust speed of that if you wanted to. Other ways of improving this, remember this is often where you are using an insulating material, so it's usually a polystyrene cup or a copper calorimeter. So to ensure an improvement, it's often how do you make sure that the temperature, the energy isn't lost. So often using lids, insulation, those factors affect your results. You might even talk about protecting the flame from a draft. So protect from draft. A draft is obviously wind causing the flame to be a bit ununiform, so it's not completely hitting the calorimeter exactly as you want. Also to ensure the heating is better, if you reduce the distance between the flame and the calorimeter, that would also improve the result. Okay, looking at practical 3, so this is to do with looking at rates of reaction. There's a number of methods that you need to be aware of: collecting gas, also looking at a precipitation reaction. I'm not going to go into too much detail because you've done those practicals a number of times. The only thing I'll look at is how would you improve, so looking at improvement of a precipitation reaction. Now the problem with the precipitation reaction is endpoint. So because it's human judgment on endpoint, that's an issue. How would you negate that? How would you improve on that? An easy way is to get a light meter. So a light meter, basically, you've got a light source, and the light source is, so you've got the conical flask, there's the precipitation reaction, and the light source goes in, and then you've got a detector here which will detect the amount of light coming through. So if the solution is completely clear, then obviously all the light will go through, but as the reaction proceeds, it becomes more and more cloudy. There is less light going through, and therefore a point can be decided on when you stop that, and then that's the time that you quote. So that's basically a simple way of getting rid of the human judgment aspect of a precipitation reaction. Practical 4 is looking at iron testing. I'm not going to, again, there's not a lot to go through here. You have to learn all the content associated with all the different positive results. The only thing I'll just make sure that you should remind yourself of is to how to carry out flame test. So just make sure that you have covered that. So using the nichrome wire, things like that, just cover that when you can. Okay, so looking at practical 5, this is obviously one of the organic practicals, so often the question comes around the method of distillation. The main thing here is the movement of water in a condenser moving in from the bottom, out from the top, from the bottom and out from the top. The question is why? Now the main reason why is if there is a slowdown of a flow of water, if it moves in from the bottom, there won't be any air pockets. So if there's no air pockets, there's more cooling happening throughout the whole condenser. So that's why if it's moving in from the bottom, it will make sure that there is no air pockets. So the whole of the condenser will be filled with water, which will keep the condenser cool. So that's why it's important to have the water moving in from the bottom, out from the top. Other things with regards to practicals associated with organic, often we use round bottomed flask. The main reason there is that it's a bigger surface area, and the bigger surface area allows more uniform heating. So that's why we tend to use round bottomed flask when we are heating organic substances. Other things, anti-bumping granules. Now you would have all used anti-bumping granules. The main reason why you use anti-bumping granule is to prevent vigorous bubbling. So it prevents vigorous bubbling. So that's why anti-bumping granules are useful. Water baths mainly used for heating a flammable solvent. So if a solvent is flammable, you'd use a water bath because obviously you do not want naked flames being used in a reaction that has a flammable solvent. Right. Other things. Practical 6 is the functional group testing. Again, I'm not going to go through all the chemical tests associated with that. What I would suggest is that other questions that I've seen come up, the drawing. So when you draw practical drawings in chemistry, the main thing is you need to make sure that you use straight lines. The common one is of a Birchner funnel. So when you draw a Birchner funnel, you've got to make sure that you include the filter paper here. So that's usually a Birchner funnel, and then you've got your flask that you need to include with a vacuum. So you've got often called a vacuum flask, and then the filter paper here. So this is your filter paper. This is the Birchner funnel, and this is a vacuum flask. So straight lines, filter paper for that's often asked. Other general thing, this is sort of very general concepts of practicals. So meniscus level, remember how to use that. It's looking at the bottom of the curve. That's the marking point that you need to consider. When you're heating things, you need to try and avoid spitting. So often they say, why would you need to heat something gently? It's to avoid any spitting. Also, when you are looking at mass change, you often heat until no mass change. So that's often another question that they ask, how would you know when to stop the heating? You heat it up, check if there's a change in mass, and you'll carry on heating it until there is no change in mass. Okay, so that covers a lot of the practical skills associated with this. I know I've not gone through any of the year 13 practicals, but most of the content is covered in the first 6 practicals in terms of practical skills.